So after recording the previous video, I actually added more proposition in the section 3.6, which are proposition 3.28 and 3.29, which is about the Hamilton cycles in tournament. So I actually put it before the proof of Maynard theorem. So on the lecture note, it comes before. And of course, the Maynard theorem already implies that every tournament is, Hamiltonian. It has Hamilton cycle because what is the Maynard theorem? It says that if we have a strongly connected digraph, and whenever these UV are non-adjacent vertices, it is satisfied and it is Hamiltonian. And assume you have a strongly connected tournament, then this condition is vacuously true because there are no such pair of vertices. So it trivially satisfies this, and we conclude that this has a Hamiltonian cycle. But without that, we can directly prove that. First, we can prove that every whole tournament has a Hamiltonian path. Just to recall, tournament is oriented complete graph. You have a complete graph, and you orient each edges in arbitrary way. Then that's the tournament. This names comes from the situation that every two player plays a game, and then whenever some player beats the other, you orient accordingly. So this tournament means that lots of player plays all possible games. So we know that every tournament has a Hamiltonian path. Here, Hamiltonian path is a path that covers all the vertices. And let me quickly explain the idea of proof. So there are several ways to prove, but one way is that you order the vertices. And you order the vertices, then the edges could be either oriented this direction or this direction. Let's say these edges are forward edges. Then for given tournament, we can either give this ordering or give this ordering. These two are actually same tournament, but we can give two different ordering. Here, all three edges are forward edges, but here all three edges are, say, backward edges, non-forward edges. So this ordering, the number of forward edges depends on ordering. And there are finitely many orderings. So among those orderings, we choose the one which maximizes the number of forward edges. Say we have forward edges, and some of them are actually backward. So we take this ordering, which maximizing the number of forward edges. Then what happens is that we can actually prove that from vi to vi plus 1, it's always forward edges, oriented in one direction. If this is true, then we just list all the vertices in this order, then we already get a Hamiltonian path. So it's enough to prove that every consecutive vertices are actually forward edges. And what happens if some of them are non-forward edges? So this is backward edge. Then what we do is we swap these two on the ordering. So we have V1, V2, and so on until we have Vi plus 1 and Vi, and so on. Then the edges now have, several types. One of them is that the edges who doesn't touch, is not incident to either vertices, are still, same. If it was forward edge before, then this is forward edge now. And if something is backward edge before, and this is backward edge now. So nothing changes there. And then there are edges which is incident to one of these vertices. Let's say if this was forward edge before, then this is still forward edge. And if this was forward edge before, then this is still forward edge. So those edges are, still same in terms of whether it is a forward edge or backward edge. But now this edge, this backward edge from V sub I plus 1 to Vi is now a forward edge. So this actually increased the number of forward edge by 1, which is a contradiction because we took the ordering which maximized the number of forward edge. So that shows that every consecutive, in this ordering, every consecutive, vertices, they have a forward edge. And this proves the proposition 3.28. And proposition 3.29 says that a tournament has, let's say tournament T has a Hamilton cycle if and only if T is strongly connected. So one direction is easy. If it has Hamilton cycle, then for whatever two vertex you take, so here is U and here is V, then you just go along with this Hamilton cycle until it hits the other vertex. So between any two vertex, we can find the path. So this is strongly connected. Let's consider the other direction. And suppose this is not Hamiltonian. This is strongly connected but not Hamiltonian. Then we can find the longest cycle C. And because this is not Hamiltonian, this C does not cover all the vertices, so there are vertices outside. Then, because of the strong connectivity between these two vertices, there must be a path from left-hand side to right-hand side. So that means there is at least one edge going from this left vertices to right vertex, say this vertex V. And now if we see, if this V, so we have V and then C, we have this one edge here. And then now if this V has a edge from V to some vertex in C, if this is true, then we check all these middle ones. And then find the one which is, so let's keep the order first vertex, second vertex, third vertex, fifth vertex. And among those, choose the minimal, one. Choose the one which is close to this vertex, say X, which is oriented from V to here. Then by the minimality, right next one is oriented the other way. Remember, this is tournament, so between any two vertices, there is an edge in one of the direction. Then now what we know is, let's say, assume this was oriented this way. Then now what we can do is we can take this cycle and then we go here and then come back. Then we get a cycle with one bigger length, which is a contradiction because we took the longest cycle. So what it means is that when we have this C and this B, then every vertex is an in-neighbor of this B. Every vertex in this C is in-neighbor of this B. But again, by strong connectivity, we should be able to find the path from B to some vertex in C. It may go through other vertices in here, but let's say, we stop at the first vertex which is C. Then, again, we can assume that this C is oriented in one direction. Then you find the vertex which is in-neighbor of this, U, and this is X. Say Y. Then again, what can you do? You can go take one turn, and then once you are here and you move to B, and then you come back. Then you get a longer cycle, which is a contradiction as the C is the longest path that we take. This shows that the C must cover all the vertices, and this proposition holds. So now we really move to the coloring in the next video.